Okay, so we're recording now. So today we have we'll continue discussion about networks. Today's lecture is actually quite mathematical. So I'll try to go a little slower over the slides. It's usually pretty challenging to follow the lecture when you have formulas in the slides, and then those formulas are you don't write them on the board, but you're just watching people talk over those formulas in the slides. And so I'll try to go slow, but let me know. Feel free to interrupt. There's just very few of us here, so I should be able to answer your questions if you have questions. All right. Okay. So what we're going to do today is we're going to talk about one particular class of algorithms, which is called graph partitioning algorithms. And this is actually quite interesting approach to graph partitioning that allows us not only to be able to split the graph into pieces and thus find clusters, but also can help us visualize data as a byproduct of the algorithm itself. We can learn to visualize data. Okay, so lecture outline for today, we're going to talk about graph partitioning overall as a problem, and we already touched a little bit upon it last time, but today we're going to dive in. And then we're going to talk about very particular graph partitioning algorithms, which is called spectral optimization. And it's called spectral because it uses eigenvalue and eigenvector computations, which is the spectral properties of the matrices, of the adjacency matrix. For those who has just joined us, guys, please turn on the cameras. I really would like to see the audience, and you'll be able to see each other. So it's kind of a little bit more of a seminar. And I see, looking at the backgrounds, everybody's all around the world. All right, now we know your preferences. Okay, so network communities. As we talked before, when we talk about network communities, we define network as a group of vertices such that vertices inside the group are more connected with each other, more tightly connected. There are more edges within the group than in between the groups. And when we looked a little bit into the problem of finding, finding communities, we actually said, okay, look, there is, for example, there are some edges, like here, this edge, this edge, this edge, this edge, that if you cut them, you'll separate this group of nodes from other groups, and so that would allow you to detect communities. And so in some sense, the problem of graph partitioning, or finding those edges, can help us find clusters within the graph. And we also discussed a little bit one of the algorithms that was called edge betweenness, and that algorithm would find for us those edges. That was one of the approaches to find those edges. And we discussed that algorithm, and we found out that yes, you can do it. It's a little bit ad hoc because there is no sort of good math behind it, in terms of there is no proof that what you find is some way optimal. And when you run it, every time you run it, you might get slightly different result. We're going to talk today about an approach that is much more mathematical and more consistent, but it is a little bit more complicated. Okay, so first of all, just to remind you that graph partitioning is actually a very, very hard combinatorial problem. And the reason for that is if you just think about dividing something into groups, there are multiple ways of doing it. That's like factorial large number of ways of doing it. The way to understand this, and let's for a sec look at this formula, where this formula coming from. If I just try to solve a very, very simple task of dividing n nodes or n objects into two groups, right? And I'm just trying to calculate how many ways are there to divide, n nodes and objects into two groups. groups of different sizes. And if the size of one group is n1 and the size of another group is n2, well, together they should form all the objects, right? But the number of ways is actually huge. To calculate this, it's very easy to sort of, think about it the following way. You can imagine that you take your objects and you kind of lay them out, right? Order in particular way. And then you can split it, right? There are some objects to the left, some objects to the right. So the question is, how many ways to order those objects? Well, there's n factorial ways to order n objects if there's distinct objects. Then when you split them into two groups, well, you can actually permute objects within one group or permute objects within another group. It doesn't really matter because they still stays within the group. And there is n1 factorial ways to reorder objects within one group and 2 factorial to reorder into another. And so the total number of ways you can actually partition n nodes into two groups is here in the formula n factorial divided by n1 factorial and 2 factorial, which means if you have 10 objects, it's actually 10 factorial divided by, and you want to split it into two groups, say one group of 3 objects, another group of 7 objects, will be 10 factorial divided by 3 factorial divided by 7 factorial. Just try it sometimes, you'll realize that it's really large number. So it's combinatorial a large number, and that's why going back to our problem, just sort of going through all the pairs or trying to just go through combinations of nodes that you think belong to a particular cluster, just going through all the possible combinations, it's impossible, right? It's just too many of them. Now, this is even when divide a network of n nodes into two groups. Now, when we do clustering or community detection, we don't even know how many groups are going to be there. So the question, we should go and try to calculate dividing into, well, some number of groups, right? From 1 to n, you can either have one node per group or pretty much all the nodes in the same group. And there is a special even number, it's called Stirling's number of the second kind that allows you to compute this. Now, we don't want to compute it, but if you just think about the total number of partitions, and I just calculated for the graph of 20 nodes, right? So if you just take a graph of 20 nodes and try to go through all the possible combinations of all the possible groupings of only 20 nodes, that's how many of them would be, right? So pretty much what I'm trying to say, it's just impossible to go through all the combinations, right? And so instead of doing that, you need to come up with some sort of heuristics, somewhat maybe a little bit ad hoc algorithms, but that would avoid this factorial large number of combinations, right? So that's the problem with all type of integer programming when you have to go through multiple combinations. And that's why people want to avoid this. Okay, so what we want to do is, well, first of all, I want to get rid of this and I don't know how to do it. All right, let's see. It still stays there. Okay, got it. All right, so we're gonna first of all look at the graphs that are quite sparse, where the number of edges is much less than possible number of edges. We'll think at the beginning though that graph is connected, so we don't have explicit sort of split communities. And we'll think about how to solve this problem, this optimization problem of finding the right combinations, the right split, by looking into optimization criterion. So what do we want to actually optimize? And then how we're actually going to optimize it. So we need to decide what we're going to optimize. And second, we need to find a way to optimize it. And as I said before, it's NP hard, which means it's the factorial large means it's non-polynomial time to solve. So it is a very hard problem. And it's usually solved by what's called greedy or approximate algorithms. And so that's what we're going to look into right now. So this is our graph that we're going to work on, that we're going to work with. And let's see what we can calculate on this graph. So last time when we discussed graph partitioning, we actually introduced certain metric that would allow us to decide if particular cut or separation of the graph pieces, is it good or bad, right? So do you remember that metric?
Modularity.
Modularity, yes, modularity was actually when we talked about already when we talked about the overall, the quality of the partitioning. That is true, and we're going to use it later on. But there was even some simpler thing we looked at when we just look at this type of graph and try to see if, for example, separating it. Let me try. I'm also learning how to use this. If we, for example, separating here, if this is a good separator or bad separator of the graph. So what did we actually count?
Was it the number of cuts?
Yeah, we counted number of cuts. So we said, okay, well, there is one cut here, second cut here, so the cost here is 2. So, it may be not such a bad cut. Or if you take a look and, if we do, say, for example, slightly different one, if we do it, say, this way, right, then there is 1, 2, and 3. So, it takes us 3 cuts to separate it. So, this partitioning like that cost us 3 cuts versus partitioning like this cost us 2 cuts, and so the blue one is better, right? Make sense? Okay, so that was sort of the most sort of simple, the trivial approach to do this. Now, but if I try to follow this logic, if I try to follow the logic of just counting how many edges I need to cut out, and the smallest number of edges that requires, that I can cut out and split the graph, if I just follow that, then I'll run into some troubles, and the trouble could be seen easily here. If I want to minimize the number of edges I cut to split the graph, right? Then let me adjust this a little bit. So if I want to minimize the number of edges that I want to cut to split the graph, then, for example, I can do this, right? So I can cut here. It cost me 1 edge, and I split the graph, right? I would say, okay, this is my one subgraph, right? One cluster, and this is my other one. Now, it's sort of obvious for you now that this is not sort of what you have in mind, right? You just sort of removed one node. What you're looking for is somewhat more balanced, right? Something like maybe that, but definitely not just cutting out one. So by looking at this, you realize that just simple cut, right? Just counting the number of nodes you remove is not a good metric. Now, how can we adjust it? How can we improve it?
Count of number of nodes in each cluster.
For example, right? Instead of just saying like, let's count, how many cuts we do, let's also take into account how many nodes we cut out, right? So here is like 1, 2, 3, 4, 5, right? So there are going to be 5 nodes here, versus if I do just cut here, there's going to be 1 node, right? So definitely, we can try to do that. So the way to do it more mathematically, and you're absolutely right. So the way to do this, I'm trying to see how I can move on to the next slide. The way to do this is to introduce metrics. So the metric that we just talked about, sort of the simplest metric here, is called graph cut, right? This is just the cut. This is just the number of edges that we remove. Now, we just realized that using only that metric leads us to cutting very small pieces. So then people introduced what's called ratio cut. Ratio cut is the value of the cut, so number of edges, divided by what's called the volume the remaining volume of the partition. And the volume is just the number of nodes. So that's exactly what you suggested, right? We take the cut, like in that case on the previous slide, the cut was 2, right? And then divide by 5, which is the 5 nodes in the partition. But to make it symmetric, we're also saying, let's do this 2, and then we divide by the number of nodes that remains into the second partition, right? Because we have entire graph. And then, so what remains there, if there is total n nodes, then it is divided by n minus 5. Okay, that's a metric. And in fact, that looks better. It actually will prevent us from just cutting single nodes quite often. But then there are even more interesting metrics, and one of them is here. It's called normalized cuts, and in fact, it's a very popular metric. It is cut divided by what's called volume for the partition. Now, volume here, it really means the number of edges that starts on the nodes within the partition. Now, it's not completely trivial, right? So here it's just the number of nodes in the partition. Here, this is a number of edges that starts on the nodes within the partition. So if we have, if we have, you know what, it's easier for me to just go back. Right, if I look at this graph and I try to calculate the number of edges that starts on some particular partition, this is how I can do it. Let's say this is our split. The number of nodes in this split here is 1, 2, 3, 4, 5. The number of edges that starts on the nodes in this partition would be 1, 2, 3. These are the edges that starts from this node. Then for the second node, there is 1, 2, 3. So it's 6. Then for this node is 1, 2, 3. It is 9. Then for this node, 10, 11. For this node, 12, 13, 14, right? So that's the volume. Make sense? Okay. So what you do by doing that is you're taking into account not only sort of balancing, you're not only balancing the number of nodes, but you're also balancing the number of edges that that remains within the partition. Okay, and that's called normalized cuts, and that's probably one of the very powerful and popular metrics. And then there's a couple other metrics, which is called, quotient. Actually, there is another metric which is called conductance or quotient cut, and it's usually people who work in theoretical computer science, they like that metric because it just, it connects to some it nicely connects to some properties, but of the graph, that sort of graph theoretical properties. But we're going to focus on using this metric a lot, and the reason for that is because this metric is easily linked to eigenvalue and eigenvector problems for the graphs. Okay, and we're going to see it in a minute. So this is a metric that we're going to work with. All right. So moving on. That was the metrics, right? So as we described, when you want to solve the optimization problem, there are two things, right? You need to select the metric you're going to use, and then you need to figure out how you're going to optimize it, right? What are you going to do? And there are multiple ways people try to optimize this type of metrics. There is a greedy optimization. There is, a lot of heuristic algorithms. There is like randomized algorithms. We're going to look into one particular algorithm, which is called normalized cuts, right? We're going to use this normalized cut, and the algorithm is called spectral graph partitioning. It was actually discovered a long time ago, 1972, then pretty much forgotten, and then rediscovered again and applied, in practical way in 2000, right? And then it became quite popular and famous. Before that, it was just only mathematicians who knew it. So we're going to look into this algorithm. Again, this is probably, so far in our lectures, we didn't dive, very much deep into the math. Here is the lecture where we do. Okay. Oops, it didn't clear it. So let's start with some very simple problem, and I'm gonna go slow, but guys, it's important for you to understand what's happening, at least on this slide, right? Later on, you know, if I lose you, you can catch up. But this slide is really important because it has sort of the general idea of the approach. So the idea is the following. Let's look at the graph. Let's say our graph looks like this, okay? It's just a line, and there are a bunch of nodes. And let's say we want to split the graph into two parts. Partition number 1, partition number 2. We'll call one partition, we'll call it, you know, plus partition, and another partition, we'll call it minus partition. All right? Now, imagine that we already kind of know the answer and we splitted the graph here. So all the nodes in this partition got labels +1, and all the nodes in this partition got labels -1, right? So far we're just saying, look, if we know how to split the graph, we split the graph into two pieces, we assign all the nodes in one piece +1s, all the nodes in other piece -1. And then I can actually describe this splitting of the graph by what's called indicator vector, which is just a vector that for every node just gives a label +1 or -1, depending on if the node belongs to this plus partition or if the node belongs to the minus partition. Make sense? Okay. Again, if something doesn't make sense, just stop me and ask. So I'm not telling you yet how we do this split, but I'm saying if there is a split, we can describe it using these labels. Okay. So now this is a very simple mathematical trick how you, by using these labels, you can actually calculate the cut or the number of edges that connects those partitions. Remember, we were looking into, first of all, looking into this cut. So how many edges we need to remove to split the graph into two pieces.
I have one question about, we have here nodes with +1 and -1. We add this is node +1, or it's the weight node?
Oh, no, this is a label. This is not a weight. This is just a label that I assign to the nodes. I said, look, if we do a graph, if we cut things into two pieces, I just call these guys, I assign labels +1 to those guys and -1 to others. So these are not weights, these are just labels. So if I go back, for example, for a sec, this is inconvenient. If I go back here and you know, try to do what I just described, so what I'll be doing is this. Let's say this is a partition. Then I'll assign to each of these nodes label +1. So each of those nodes have label +1. And everybody here, every single node will have label -1. Okay? And then what we're going to do right now with mathematical formulas is we're going to try to calculate the cost of this cut. So by, you know, we assign those numbers here, and then I'm going to do some mathematics. By knowing those numbers, I will calculate that it takes us 2 edges to, it costs us 2 edges to separate the graph into 2 parts, right? That's all we want to do right now. Make sense?
We will restore which edges we will cut, or just the number?
At this moment, no, okay, this is a good question. At this moment, it's only a number. So what I'm trying to say is, like, imagine that we know how to split the graph. If we know how to split the graph, I can calculate how much it costs me, right? Let's say then there is, and if I provide this split, the formula will give me an answer is going to be equal to 2. And if I provide, this split and give the assignment, the formula will give me the answer 3 because it takes 3 edges to split it into this. So this, again, this is not yet, this is not explaining how to split. It just says if there is a split, how to calculate what it costs, right? Because here on the picture, we just look at it and say, oh yeah, there is 1, 2, 3, right? But if you cannot draw the graph, is the graph too large, you cannot use your eyes, how do you compute how much it costs you to split, right? How many edges crossing. So pretty much the cost of the split is how many edges crossing this boundary in between 2 groupings. Okay, so let's take a look here at the formula. So as I said, we're doing the split. Here is the partition. These are -1 nodes. These are +1 nodes. So the idea is the following. We assign to every node this label, and now we have a vector of those labels. So let's write the following formula, and let's understand why this formula is actually calculating this cut. Look, what I'm doing here is the following. I'm saying, let's take this indicator vector and go through all the nodes that are connected by edges, right? So we go through all the edges and we look at the nodes that are connected through edges. And let's calculate this Si minus Sj, where S is that indicator vector and I and J are the indices of that vector. So let's just do it right now. We go from left to right, and we'll take this node. We take this because here is the sum over all edges. So we're going to take this edge first. This edge first. There is one node. There is another node. Each of them has the value -1. So what is the value of this difference?
-2.
No, it's not -2.
Oh, no.
It's 0, right? It's -1 minus -1 is 0. Now, if I take this edge and calculate this number, it's going to be 1 minus 1. So it's +1 minus +1 is 0. For this pair, it is +1 minus +1 is 0. But for this pair of nodes, it is -1 minus, again, 1. It's going to be -2. Then it is squared. It's 4 divided by 4. It is equal to 1. So what I'm saying is that this formula, using this indicator vector, tells us precisely the cut in the graph. So the reason for that it works that way is very simple, because again, all the nodes that belongs to one partition has the same label, and I just subtract them. All the nodes that belong to another partition also have the same labels. So it's +1s and here it's -1s. So within the partition, this difference for each partition, it's equal to 0. And this difference is non-zero only for the edges that connects two partitions. Does make sense?
So
Yes.
we take in account each node or each edges 2 times or 1 in this case?
Good question. So right here, we counted only 1 because here we're summing over the edges. But then when I go to the next formula where I say, okay, look, let's, instead of just counting edges, let's actually introduce back adjacency matrix and counting through the nodes, then we will double count edges, but to compensate for it, instead of 1/4, there will be coefficient here 1/8. Okay, so here we just count them once, but when I move to the next formula and putting back adjacency matrix, then it will, you know, double count, and that's why I will have to divide by 2. Now, the only thing that happens on this step is instead of summing over edges, I start summing over nodes and put here adjacency matrix. And remember, adjacency matrix has zeros. Oops. Well, adjacency matrix has zeros where there is no connections, right? And have ones when there are connections. And so instead of summing, going over all the edges, I go over all the node pairs, but within the sum, it's only those that are connected have ones, and so that's are the only nodes that contribute to this. Now, guys, this is not complicated math, but I do recommend you take a look at it on your own if I lost you a little bit in here. All right, but overall the idea is very sort of straightforward. We assign labels to each partition. When we assign labels to particular partition, we can actually then calculate the difference in between in between those labels, and that difference for the nodes within partition will be equal to 0. The difference in between the nodes within each partition is 0, but the difference in between the nodes that belong to different partitions will be equal to the number of edges that connects those partitions. All right, are you still with me?
Yes.
Okay, good. All right, so then then this is part of like bigger story, but this is a sort of important starting point. Then we're going to do some sort of very simple, very simple, calculations. I don't want to go through them in the details, but what you can do is you can add sort of additional trick here. An additional trick is introducing what's called delta Kronecker symbol, delta ij, that is equal to 1 if I equal to j and equal to 0 if I is not equal to j. That just sort of, a way to reformulate a little bit the sum. So this is the way it is written. Introducing this delta symbol, I can write it in the following fashion. And this one is, in fact, if I go back to matrix notation, is the following. And this is what we want to understand. So what we're saying is the value of the cut, when you split the graph into 2 pieces, can be calculated the following way. When you have the split, so you do have the values Si and Sj, you just take them, multiply them, and you multiply them by this difference. This difference is here, this is adjacency matrix, and this is a diagonal matrix. So you take a diagonal matrix and subtract the adjacency matrix.
So typically the identity matrix, or is this some other diagonal?
No, okay, that's a very good question. It's not just identity matrix. It is, look, this is what it is. It is their identity matrix diagonal scaled by node degree. So it is the matrix D, it's diagonal, where on the diagonal you have node degrees. And this matrix has a very, has a name. It's actually called Laplacian. And we'll meet this matrix, many times later on. And those of you who actually you probably guys had some differential equations classes, right? Partial differential equations. And then you probably heard about Laplacian operator and, Laplacian. Have you heard about Laplacians?
Yes.
Yes.
Yes. So this is, yeah, so this delta squared, right? Which is Laplacian. So what we see here, this one is a discrete representation of Laplacian. So if you want to take Laplacian operator and discretize it on the graph, that's what you're going to get. And if you try, I don't know, have you had a numerical methods where you solve partial differential equations with like finite difference schemas? Have you
Yes,
done
I
that?
did.
Yes.
Yes, so that's exactly what you did. So this is a generalization of finite difference. In finite difference, you just take, you think about a grid and you take, you know, to the left, to the right, up and down, right? When you calculate finite differences. This is a generalization for any type of matrix, for any type of graph, where you don't necessarily have a regular mesh, okay? So that's called Laplacian operator. And that's how it's sort of, that's how we can actually introduce it here. All right, so next step is, you know, that's what it is. That's what it looks like, in fact, Laplacian operator. If I take the same one-dimensional graph, it's again called, this is called graph Laplacian. And, you know, it's a difference in between diagonal matrix that has degrees in there minus your adjacency matrix. Or you can actually just define it as a matrix that has minus ones where there is an edge and it has no degree at the diagonal. And so if I, for example, take this graph and write a Laplacian matrix for this graph, this is what's going to look like. So it's going to have, you know, the minus ones here, because those, they coming from, you know, edges, all these edges from the adjacency matrix. And on the diagonal, you'll see 1, 2, 2, 1, which is corresponding degrees. And notice the important property of the Laplacian matrix that, what's the property, by the way? What, you know, by looking at this matrix, what you can, what property can you instantly think of? If you look at every row.
Трехдиагональная.
It's okay. So first of all, there's diagonal here, yes, and it is like 3 diagonals. But there is something else. If you look at every row, there is something else that should jump.
It will sum to 0.
Exactly. So every row and every column here is going to sum to 0, right? And that's a property of Laplacian matrix, an important property. In fact, because of that, the eigenvalue, the first eigenvalue, is going to be equal to 0. If you remember a little bit of linear algebra, right? Again, if you ever done, you know, partial differential equations and did it numerically and actually did the finite difference, you should recognize this as a very typical, you know, finite difference matrix for Laplacian operator, right? If I try to solve, you know, any Laplacian sort of heat, for example, transport on a grid, right, that is being described by Laplacian, by partial differential equation by Laplacian, that's your Laplacian for that, okay? All right, now, but that's physics, right? Here we don't talk about diffusion. Here we don't talk about, you know, heat propagation. Here we talk about, you know, calculating, you know, finding partitioning of the graph. But it happens that, you know, the cut, the value of the cut is can be computed through the Laplacian operator. And it's not an accident. There is a, you know, quite deep connection. But the point is, again, coming back here, what we see is that the cut is actually, this is Laplacian matrix. This difference is Laplacian matrix. And so you take Laplacian matrix, you multiply by our indicator vector, Si as j, sum over all ij, and that gives you the value of the cut. Okay? So it looks like a magic, but, you know, it's very sort of quite simple math. Okay, so let's move on. So why do we want to do it? Well, the reason is the following. Now, I know how to calculate the value of the cut. So if I have a matrix, I can calculate the value of the cut if I have this Si as j, right? So if I have assigned nodes to belong to one partition or to another, then I can calculate that cut. And this is how I can do it, right? It is, you know, if I write it down as a summation, that's what it looks like, or if I write it as a matrix multiplication, S is a vector, S is a vector, so, you know, column vector, row vector, and this is Laplacian matrix. So why do I want to do it? Well, the reason is the following. If I know this S's, I can calculate this number, right? I can calculate the cut. So if this is known, where is my notation? So if this is known, I can calculate the value of the cut, right? But what I want to do, in fact, is slightly different. I want to say, look, let's try to find the values of S such that the cut is minimal. So now, if I know how to compute this, I can actually try to go through all the possible S's and then select such an assignment of S's that will make this number smallest. Okay? And so that will allow me to find the best partition.
Why we are not taking account the number of nodes or something like volume in this?
We'll do. We will. I mean, we will do in a second. I just wanted to explain this on a without that, right? How it works just for the cut, and then we'll do it for normalized cut. So this one will just find the cut, right? And the idea again, you know, you just need to find the minimum of that you know, value of this sum with respect to S. And I can also, you know, I can also put some constraints on this because I want to make sure that S's, you know, have plus ones and minus ones. So I can actually try to, I can add here constraint, and I need this constraint later on, that, for example, they add up to 0. Now, if I force them to add up to 0, I'll create balanced cuts, which means the size number of minus ones is approximately equal to, or should be equal to the number of plus ones. Now,
excuse me, is it possible to get several S's which minimize the Q?
yes, so the this is that's actually a good question. This is quadratic, right? So there will be only one. In this case, it's going to be only one, you know, correct S, but it's not clear how to find it. And here is a problem. Remember, we talked about this. You know, what we started with is that these are integers. And though I formulated this as optimization problem, and I didn't make any approximation, I just said this is an optimization problem, I still will not be able to numerically solve it because these numbers are integers, and since they're integers, you cannot differentiate, you cannot do anything, right? So what would we, but there is a way out. And that's what Fiedler came up in 1970. He said, like, okay, you know what? We cannot solve this precisely in integers. When S's are integers, plus or minus ones, we just cannot do it. It's mathematically impossible because a factorially large number of those combinations, and I need to go through all of them. But if we take those S's and for a second imagine that S, right now S belongs to integers. But let's replace S or decide that S can be a real number. Now, if we say that, you know, it's not a label anymore, right? It's not plus or minus 1 anymore, but we will deal with that. But if we do that, this just becomes a quadratic optimization problem. And in the continuous real domain, solving it is easier. You just take a derivative, equate it to 0, and you're done. Now, by doing that, you're not going to solve precisely your integer optimization problem. But you can take your solution then and kind of round it up to the nearest integers and said, hey, this is your answer. Now, this is a point going from integers to real numbers where we approximate, right? We cannot solve up to this point, this was a precise formulation. This is how you compute cut through if you have plus or minus 1 labels. The problem is we don't have those labels, we actually need to find them. In order to find, if we want to do it in an honest way, we literally need to go through all the possible assignments of 1s and plus 1s and minus 1s and find the assignment that gives us this value the smallest. But that's factorially large number of combinations, we cannot do it. So what we're saying is, screw it. Instead of just doing this integer, going through all the integers, we'll replace them with real numbers. Then this is just a quadratic optimization problem. We solve it, the usual easy ways with Lagrange multipliers, and then we'll round up the solution. So instead of doing integer optimization, which is in p-hard, we approximate it with real numbers, and we're solving a proximate problem. All right, I pause here for a second. Does this make sense, what we're trying to do?
I have a question about balance constraint. Is it a hard constraint? I mean, for example, if we have odd nodes or...
Very good point. So I put here this constraint for an integer programming. We're going to relax it right now when we, we'll relax it on the next slide. Okay. So again, guys, this is probably the most mathematical lecture out of all we have. So what we're doing is we're switching from a discrete problem that is in p-hard to continuous problem, which means instead of trying to do this minimization under constraints that each s, a label, can be plus 1 or minus 1, and the sum is equal to 0, we are replacing it by what's called relaxation, or by relaxed problem. And so instead of that, we're going to be solving this minimization where x, and I don't know why I didn't write it, is just a real number. Here s is an integer. Here x is a real number. And we're going to change constraints a little bit. Instead of making each of these s's that were plus 1 or minus 1, we'll force the sum of xi squares to be equal to n. So if, for example, we had only 2 labels, let's say we had only 2 labels, then the possible combinations of the labels would be, the s could take, for 2 nodes, could take values 1, 1, 1 minus 1, minus 1 minus 1, and minus 1 minus 1, right? What we're doing here is saying, look, instead of s being able to be only those 4 points, so if we had, I would call it s, it's 1 node, and that's sort of the second node. So s's would only be, and this is 1, 1, minus 1, minus 1, and 1. So s's could exist only, the s's could exist only here, here, and here. What we do instead right now is replacing it by real values. And replacing it by real values, we're forcing real values to satisfy this constraint, which in this case would be x1 squared plus x2 squared is equal to 2. which means we're just saying we're looking for the solutions that lies, oops, yeah. I was trying to draw a circle. Circle that goes through those 4 points, and it's impossible to draw it with a mouse. But you guys understand. So what we're trying to do is, instead of just saying, you know, only those points are allowed. Oh, how did that work? Okay, thank you. So instead of just having those four points, right? We're putting everything on a circle, and we're saying, look, these are solutions that are possible. All right. And then after we solve this optimization problem, we just say, okay, look, let's round it up. And we'll just do very simple rounding up. We say, okay, if xi, the one that we get, is greater than 0, we'll call it +1. If it is less than 0, we'll call it -1. All right? And that's the trick. So I think we are done with this part, and let's just solve it. Now, solving it, you're probably familiar with Lagrange multipliers, right? Come on,
Yes.
Lagrange multipliers, yes. So if you have optimization under constraint, you have a function that you want to optimize and you have a constraint, what are you gonna do? Well, very easy. You take that function that you want to optimize, right? And this is our, remember, you know, that's the Laplacian function, Laplacian matrix L, and those two vectors. The vectors now that you know, instead of integers, we have real numbers. And then this is a constraint that sum of all xi squared is equal to n, right? And then you combine them through Lagrange multiplier and solve this optimization problem. Now, if you take this and, you know, kind of with Lagrange multipliers and matrix algebra, it's kind of funny. These are vectors, but you can still differentiate with respect to the vectors, like you would differentiate with respect to numbers. And so you can take this derivative, equate it to 0, and that will instantly become that, right? Because differentiate with respect, for example, x transpose. If you differentiate with respect to x transpose, this goes away, this goes away. You're going to get, you know, this formulation. And what is this? That's an equation for eigenvalues, right? Eigenvalues, eigenvectors. So Lagrange multiplier is eigenvalue, and our index vector, the one that are going to tell us what partition our node belongs to, is an eigenvector, right? Now, there is a constraint that remains there, and this constraint says that sum of all x's, so this one, is sum of all x's equal to, has to be equal to 0, right? That sort of allows us to balance it. And that's it, guys. So then we just do the solution. Now, if you remember, and I mentioned that before, that Laplace matrix has this interesting property that the first eigenvalue is equal to 0. The reason for that is because every row sums to 0. So the first non-zero eigenvalue, so the first smallest eigenvalue is equal to 0. The first non-zero eigenvalue or second eigenvalue is non-zero. And second eigenvector is that what you're looking at. And so this is this eigenvalue and this eigenvector, that's what gives you partitioning. Let's see how it works in practice. Let me first show you how it works, and then we'll go back to the algorithm. So this is a graph, and this is again the same graph we looked at, you know, multiple times before, right? The quadratic graph. And I calculate second eigenvalues and second I'll calculate eigenvalues, eigenvectors. Now, the first eigenvalue as supposed to be is equal to 0. The second eigenvalue is equal to 0.2. And here, every point is a node, right? And it's a vertex of the graph, and here are the numbers, right? I just show you all the vertices from 0 to this 30, whatever it is, 34 vertex, right? And on the y-axis is the value of the value of the second eigenvector. So, you know, the first node has this value, the second node has this value, the third node has this value. And again, this is just a vector that corresponds to second. It's a second eigenvector, right? And these are the values of the nodes that we get there. Okay, so our idea, what it's saying is the following. These are x's. Remember, we wanted to have those labels. So what we're going to do is we do the following. We say, okay, this is 0. Everything that above 0, every node that is above 0 will get labeled +1. And everything that is below 0 get the label -1. Okay? And then what I'm going to do is I'm going to just take every node here and, you know, since +1, I don't know, I'll call it red. And I'll take every node here. I call it blue. And show you on the graph, right? Okay, let's do it. Ta-da! Miracle, right? Magic. We did some sort of calculations, and then eventually the math actually worked. Surprisingly, you get a pretty good partition of the graph. All right. So let me again go over what we have done. We took the matrix, we took the graph, we calculated, you know, we took the adjacency matrix. Then we computed Laplacian matrix. Then we said, okay, look, you know, there is a vector where, you know, that corresponds to the nodes, right? So we take Laplacian matrix, and we calculate eigenvalues, eigenvectors. Then we take the second eigenvector, the second smallest eigenvector of Laplacian matrix. And the values are the values that we have there. Some of them will be greater than 0, some of them will be less than 0. And then what we're going to do is, for those that are greater than 0, we assign label +1. For those are less than 0, we assign to those nodes who has values in the matrix in the vector greater than 0, we assign label +1, less than 0 label -1. That's it, we're done. And that's the partition we're going to get. Does it make sense?
Could you repeat, please, about relaxation constraints problem? Because I don't understand. So we at constraint x² is equal to n. It's mean, okay, x, it is 1 or -1, okay, squared. It's mean these constraints satisfy all time.
Yeah. So what we did is the following. We said it's right here, right? So this was the original problem, the way we set it up, right? So the original integer optimization problem, this is what we're going to optimize, right? This gives us a cut. And then we said the constraints, each label is +or -1. And the second constraint that was kind of forcing a balanced cut, it says that sum of all SI is equal to 0, which means this actually, if it is exactly satisfied, then this will make your number of nodes in positive and in negative partitions equal, right? So, but we're not solving this. Instead, we're solving this problem. Okay. Now, we replaced integers with real values, and we're replacing this constraint with that. So instead of each label being +or -1, we're saying now that the sum of the squares of the labels has to be equal to n. where n is a number of nodes. You know, think about this. What it says, if we have two nodes, for example, it says the sum of the squared of the labels has to be equal to 2. So if, for example, label is equal to 1 and minus 1, this works, right? It satisfies it. But it's also more relaxed than original constraint, because if x is equal, I don't know, 0.7, and one x is 0.7, the other x is something else, you can still make it the sum of the squares is equal to 2, right? This is just more relaxed constraint. And instead of this constraint we kept, sum of si equal to 0, we replaced it by sum of xi is equal to 0. Again, xi now not an integer. So if this constraint actually forced the partition to be precisely balanced, because it's only minus 1s and 1s, and for this sum to be equal to 0, the number of minus 1s has to be equal to the number of 1s. This is not true anymore. This kind of relaxes that, because you can have, you know, the xi's can be greater than 1 or less than, greater than 1, greater than 0, less than 1, less than minus 1, and so it's not necessarily, does not necessarily converts into equal number of nodes in both clusters. That is explain the constraint.
So if we have two constraints, in Lagrange equation should be to add with lambdas.
Very good point. We could do that, and we in fact actually done it. We just done it slightly differently. Let me go show you. So what we done is the following. We put one constraint into here, and we kept second constraint right there. Okay? So this constraint that we put here led us to eigenvalue problem. This constraint, we just keep it to the side right now. Now, this eigenvalue problem has, you know, I mean, we can solve it, and there is eigenvalues and eigenvectors. Now, this constraint that came from, you know, what we just discussed where it came from, says that x has to be, the vector, has to be orthogonal to the vector of ones, right? Because this is what it says. X transpose times vector of ones equal to 0. It's the sum of all x's is equal to 0. Okay? So if that's the case, that automatically makes us to have this constraint satisfied, right? We need that constraints removed the first smallest eigenvalue. Okay? Because the smallest eigenvalue, where lambda is equal to 0, has an eigenvector of all ones. Since we got so deep, let's get let me just show you. Okay, here it is. Look at this matrix. It's just an example, right? Look at this matrix. This is a Laplacian matrix. So can you think about eigenvector that corresponds to the 0 eigenvalue? The eigenvector here is going to be lambda x, I'm sorry, Lx, right, equal lambda x. So if I take here a vector of, what kind of vector will be an eigenvector here, for sure?
All ones.
All ones. So if I take a vector of all ones and multiply by this matrix, what do I get? I get 0, 0, 0, 0, 0. So it's going to be 0 times the vector of ones, right? So vector of all ones corresponds to the smallest eigenvalue. And it is eigenvector, right? Corresponding to the smallest eigenvalue. All right, remember this. Now, going back to or forward to our constraints, this constraint, the second constraint, the one you were asking about, where is it? This one. This one. It prevents us from using this solution. It prevents us from using the lowest eigenvalue and lowest eigenvector, because lowest eigenvector consists of all ones, and we're looking for the solution that is that orthogonal to all ones.
Okay, but why don't we just say don't use the first eigenvector?
And yeah, that's pretty much what we do, right? So this solution is don't use the first eigenvector. I mean, this constraint. It literally, that's what it says. We're not using. I mean, what I'm saying is not using the first eigenvector coming from this constraint. That's all. All right. Did I answer the questions like in terms of like where all the constraints went to?
But this eigenvector not only corresponds. It seems like it not only corresponds to ones, all ones, for example. So,
I'm sorry.
for example, we have.
I cannot hear you.
Yeah.
Can you try again? Yeah, we cannot hear you. The mic is really not working well.
Is better now?
Okay, yes, it is.
So, for example, if x is a vector which has almost all ones and 1 minus 1, it's also bound by this condition, but it's not a all ones vector. And basically, when we have.
Why is it bound by this condition?
Because its cross product will be like n minus 1 ones minus 1, n minus 2.
Just give me 1 second so I would understand. You're saying, let's say we have multiple, a lot of minus 1. Can you please repeat again? We can hear you, but I can't.
If x is, for example, almost all ones and 1 minus 1.
Okay, so all almost ones and 1 minus 1, then what?
And then the cross product with unity vector is n minus 2, right?
Then cross product with unity vector is, yes, it's n minus 2, yes.
So we ban it also. We do not only ban vectors which is all ones or all minus ones. We also ban vectors like this because this condition says cross product should be 0 only.
But this is a dot product. If I multiply it by all ones. Oh, I see what you're saying. Yes, you're right. But remember that, I mean, you're right. We remove, we remove some other,
I don't understand in general, why do we need in original problem? We relax this problem because we cannot efficiently solve original one. So we want to solve original one.
Correct.
Why do we need a balanced cut condition in the original problem? Say we have a graph which is basically 2 clicks, 2 complete graphs, one with 120 nodes and one with 10 nodes. And these 2 clicks are only connected by 1 edge. Clearly, the best division is just cut out that 1 edge and have 2 clicks. But this balance cut constraint in the original problem, even with even number of nodes, it forces cut to be in the biggest click. However, it's clear that biggest click is itself a community.
Right. So look, you're correct in terms of this particular constraint, right? And we in fact you know, that's why we relaxed it, but we still need it, you know, to get rid of that eigenvector. But to solve, you know, to answer on your concern, remember that though we started with, and I'm just showing you this formulation with SLS, right, with just Laplacian matrix and cut. Eventually, what we're going to do in practice is, so right now we're actually doing just this. Come on, where is my annotation? So we're doing just this, right? But what we want to do in practice is not this, we want to do that. And so that will help us solve for, you know, your concern about, you know, cutting out just, you know, creating very imbalanced cuts. But I agree, you know, the reason for our original, you know, for this original constraint, where is it? Here is, you know, this having it balanced completely, you know, we don't need it, but relaxing it, it actually helps us, and it doesn't hurt us. Now, the biggest challenge, honestly, is not there. The biggest challenge with this method is right here, because this rounding up, or like rounding to, you know, converting those x's into integer values, this is something that, you know, not proven to be true or you know, whatsoever, right? It is just our notion that, look, we think that is that should work, right? But there is no real good proof that, you know, the way we proved everything else, that this will work. In fact, it works in most of the cases, but not always.
Also, I see why we need to constrain sy equals plus minus 1 in the original problem. It's just like idea of labels, class labels. But in the relaxation constraint x, y square sum equals n, it seems like it always could be satisfied. We could just set any solution and divide it by sum of squares and multiply by n and get new values for x, y, xi. So is it really a relaxation? Because I see that we needed to get into the eigenvalue problem to get the derivative of x equal to some constant value lambda. Otherwise, we will not have it. But is it really a relaxation, or is it just an additional condition which is always satisfied, but it helps us to get into reduce the problem into well-known one?
So the relaxation in the sense that it's relaxation in the sense that we go, first of all, from you know, from discrete to continuous, right? And so we're opening up from integers to real values. And the second is because instead of this constraint, which will have only plus minus ones, right? We allow it to you know, take you know, any values, right? Now, but why we need constraint? The reason is because otherwise, if we don't put any constraint here, the numbers, the x's, can become, you know, can grow as large as they want, right? There is no then way for the system to, you know, to control for the size of the x's themselves.
So it will not converge, or it will, or with the values are
blow
just
up.
big.
It might not converge at all. You know, it can grow or become whatever, right? And you will not be, and you will not even have like an eigenvalue problem without it, actually, right? So the point is, again, guys, the point here is that I tried to. I probably wasn't very clear. The drawing is come on. This drawing, right, where I try to say, like, if we have a two-dimensional problem only 2 dimensions. Let's say we have only 2 nodes, node 1 and node 2. And if we're dealing with S's, we can only have those 4 possibilities, right? That the first node has a value 1, has a label 1, the second node has a label 1, right? First node has a label 2, second node has a label, I'm sorry, first node has a label -1, second node has a label +1, right? Then it is -1, -1, and 1, -1, right? That's if you have 2 nodes, right? That's the 4 possibilities you have. Now, if you relax this and have it as x's, if you don't have this xi squared equal to n, then this will not be relaxation of this problem, because having xy squared equal to n, it forces, in this particular case, sum of all xi squared, in the case we're discussing, is going to be equal to 2, right? So we're going to force all the possible solutions to go through this circle. So those si's still lay on that circle. So the integers are the part of our solution, of real solution. Otherwise, you could have, your real solution be here or anywhere. If you don't have this, if you don't put this constraint equal to 2, for example. So you need to have some constraints. Otherwise, this problem, otherwise you will not be able to, optimize. Think about this. All right.
Can you?
Almost out of time. Sorry, guys. Let me just show you a couple other things, and then we get back to questions. Couple more things. In terms of algorithm, how it works. Remember, we are actually, we talked about this, that, the way what I showed you so far only works with cuts. And I said that in real life, we want normalized cuts. Well, if you actually repeat everything we've done, the derivation, but instead of just looking at the cuts, looking at the normalized cuts, right, the cut divided by the volume, you will see that the only difference it makes is that for minimal cut problem, the one that we described and solved, it leads to this eigenvalue, eigenvector problem. Normalized cuts will lead to this problem. So the only difference would be that in normalized cuts, on the right-hand side, instead of just having the regular eigenvalue problem, you have what's called, I think it's called generalized eigenvalue problem, where on the right-hand side, you also have a matrix, but this matrix is a diagonal matrix with no degrees on the diagonal. Okay, so for normalized cuts, it is this equation. But then the actions are exactly the same. All right, now there are a couple other very, very interesting properties here that really worth mentioning. As I said, yes, let's do this. We can get vectors. We can get the second eigenvalue. We can take and split it. Split it above 0 and below 0, right? And say that these are partitions. But there is something else that we can do. And this something else is, what we can do is we can take the vertices of the graph and permute them, reorder them such a way that reorder them by the eigenvalue, right? So I can renumber them such a way that every next vertex have a higher value in eigenvector within the eigenvector, right? So I take eigenvector and I just permute nodes, okay? So I renumber them such a way that the further, the larger the number, the higher the value in eigenvector. And it actually leads to very interesting things. So this is what it looks like. And now what I do is I just, again, as I said, I just permute them such a way that I, sort them by increasing eigenvector value. Okay? Notice what happened. There are two things happened. Well, first of all, yes, they're increasing, right? Well, but that's sort of, yeah, I permuted them that way. Now, you're actually noticing that there is a gap here around 0. And then there is another gap here. And this gap is, pretty big. This is also actually decent size. So one can actually show that the quality of the separation of the graph depends on the size of this gap. If the gap is small, you don't have a very good clustering. You don't have very good split. If the gap is large, you have a pretty good split. It also tells you that maybe in this graph, you might have actually two partitions that you can do. You can split here, you can split there. In fact, there is a sort of expansion of the methods that says, like, instead of just doing this rounding up, from the sign, right, just saying x greater than 0, x less than 0, instead of that, look at the sorted values and see if they group into the groups. And then, for example, this will be one partition, this will be second partition, this will be the third partition, okay? So there are a lot of papers actually dedicated to this. It was a very popular approach of clustering eigenvalue, clustering the values within the eigenvalue. Finally, what's also very interesting happens if you take this ordering and actually apply it, to the adjacency matrix, right? Remember, there is an adjacency matrix, and what we can do is we can renumber the nodes of the graph. Literally, what I'm doing here is I'm renumbering the nodes of the graph such that the nodes, consecutive nodes, belongs to the same partition, right? And then there is, so if I literally what I done, I renumber, I said like node 1, 2, 3, 4, 5, 6, 7, blah, 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 up to 20 belongs to one partition, and 21, 22, 23 it belongs to another partition. That's all done here. So if I do what I just said, and I permute, oh, yeah, I'm gonna skip this for a second. I permute those graphs, I permute the matrix, I'm gonna see that. So what's happening here is on the left-hand side is the original adjacency matrix. And you remember in adjacency matrix, non-zeros, the dots corresponds to non-zeros. Now, I can run this eigenvalue, the Laplacian matrix, right, normalized cut, and without splitting the graph into the clusters, I just renumber the nodes according to the eigenvector, and I permute matrix, I permute rows and nodes, rows and columns of the matrix, such a way that any further rows and columns, they follow increasing eigenvector size. And when I do it, you're gonna see this. So that was our original matrix. This is a permuted matrix. And what's going to be happening, you'll actually start seeing clusters or communities in this graph very, very clearly. So this method actually also becomes a very powerful visualization method. All right, now we are out of time. We're going to get back to this topic and repeat a little bit more next time. There is, a little bit more of what that we can investigate and learn about this eigenvalues and eigenvectors. It is, very powerful approach to finding, graph partitioning. Now, you had some questions. Go ahead.
Just to clarify, we use our second condition, so second restriction, to avoid zero eigenvalue. And do I actually check this condition for the second eigenvector? If it doesn't fit to it, what do I do? Do I get the third?
The second, the interesting part is that's also part of the spectral theory, that the number of zero eigenvalues, right? So the first eigenvalue is 0, right? The first eigenvector is 1. So the number of eigenvalues that are equal to 0 is actually equal to the number of connected components of the graph. So what it means, if the second eigenvalue is 0, then you actually have a disconnected graph.
That is not what I asked. I mean, we're looking for a vector. We want to find a vector.
Yes.
And we have a condition that this vector must be, orthogonal to this one.
Yes.
So the second eigenvector may not fit to this condition, or will it always fit to it?
Oh, okay. That's a good question.
I think it always will be, because first eigenvector is a unit vector. So first eigenvalues is 0, eigenvector is unit. So second eigenvector will be orthogonal.
Right. Second, that's correct. Okay, that's exactly. So pretty much, remember. Yeah, you're right. So the the eigenvectors, right? They're forming a basis, right? So they have to be orthogonal to each other, right? So that's why it works.
So I have a question: how to generalize this when we want not two partitions but more? You say like separate in graph. But
so there are. There are several ways of doing this, right? So one way is, as I discussed, there is a popular way is actually just doing this, right? Trying to look at the second eigenvector values and trying to find gaps in them, right? And sometimes people actually look at the second eigenvector, for example, third eigenvector, fourth eigenvector, and try to find clusters of nodes, right? That's one way. But honestly, the most robust way I guess I'm skipping a bunch of things. We're gonna talk about them next time. But the most robust way is this way, which is what you do is you do divide and conquer, a recursive partitioning. So you take your graph and split it into two pieces. And then you do exactly the same with each of them. And so pretty much you always just split the graph into two, and you just keep cutting it until you find out that the size of each piece either too small, right, for you, and you don't want to cut it, or it becomes too dense. So that's the most robust way.
So it's not clear how identify the stop criterion. I mean, if graph have 1 billion nodes, we can split it.
You can, okay, there are several ways, right? One way is you can say, okay, look, I mean, it's a good practical question, right? One way you can actually say, look, you know, I'm not allowing the size of my subgraph to become less than, you know, 1,000 nodes, right? Or 100 nodes, whatever. Or I'm not allowing it to have less than X number of edges. That's one way, sort of brute force way. But then there is actually a more interesting way is here. Let me get to this. Here. Notice that the second eigenvalue is 0 for disconnected graph, and it is 1 for totally connected. So if your graph, you know, when you start cutting your subgraph, you get to the point where it's totally connected, it's clear there is no reason to cut it, right? Because it's totally connected. So what you can do is you can monitor this lambda2, and when it gets large enough, which means your graph is becoming dense enough, you know, you stop cutting. So for each partition, right, you go in depth and you say, okay, let's say monitor lambda2, and if lambda2 is greater than, you know, 0.6 or 0.7, whatever, I don't cut it anymore because that's dense enough, right? That doesn't have good partition in there. But this is all literally sort of ad hoc methods that you try, you know, when you work on those things. There is no sort of solid math behind it. Okay. All right. Good. Look. Yeah.
If subgraph becomes more densely connected from 0 to 1, what happens when lambda2 is more than 1, between 1 and 2?
But I don't know. That's a very good question. I'm actually surprised to see that it's between 0 and 2. Let me check on this. I don't, guys, honestly, I don't remember. That's a good question. Don't know the answer. But you know, there are one other thing is, which is, you know, this lambda2, the eigenvalue has, you know, very deep meaning in all spectral graph theory. And, you know, there are a lot of graph properties that are related to it. Like, for example, here, you know, lambda2 allows you to estimate the graph diameter, and there are other properties that you know, connect graphs, you know, connects like sort of known graph properties with the property of the matrix. But yeah, let me check. I honestly don't remember, but good question. Okay, look, there is a bunch of stuff here left. I mean, we went slow, we dived deep. I hope you understood, you know, the method. We're gonna come back to this next lecture and go, you know, over a few variations of that method, how it is actually used, or this approach used to deal with modularity. Okay. All right, good. Then this is it for today. Thank you, guys. And stay safe, stay calm.
Thank you.
All right.
Goodbye.
Bye-bye.
Bye.
Bye.